So we're talking about NLP modeling in today's lesson, and let's focus on the big idea. The big idea of modeling here is to determine what a document is all about, what a corpus is all about, and more specifically, which words are important or not. And when we talk about, in spoken English to another human being, we say if a word is important or not. How do we express that importance mathematically? Right? That's a principal problem that modeling is trying to solve, is determining the importance of words. And when we talk about importance in terms of machine learning, we're talking about weights, right? We're talking about weights of words. So we talked about a little bit about stop words like the, and, I, me, right? A lot of these stop words, they don't add any extra value. So when we remove a stop word, what we're doing is we're saying that its weight is 0, right? To the document. It doesn't add anything to the document. The, an, a, etc. They don't add anything. So their weights are 0. And that's kind of a manual process. If we add our own stop words, it's an automatic process if we rely on NLTK's library. But the main task here, the whole hokey pokey with NLP modeling, is determining weights of each word relative to the document to answer that question, the English question: is this word important or not? That's what we're doing. Okay. So zooming in a little bit more, I'm going to introduce our dramatist persona. These are our characters in our play. These are our new key terms, our new vocabulary terms. We're going to use the term frequency, and you're going to see that expressed as TF. You'll also see the term bag of words, which is fun to say. And in fact, a word cloud is a visual bag of words. We're going to talk about a topic called inverse document frequency. And then we're going to put together inverse document frequency with term frequency and have our measure of how important a word is in a document. Okay. So let's zoom in a little more into each one of these key terms. So term frequency is a pretty direct way to measure what a document is about, right? All we're doing with the term frequency is counting the number of different words in a document, right? That's it. Exactly what a word cloud is doing visually. The challenge with term frequency, right, is that we are overemphasizing common terms, right? Because they're frequent. So if we leave our stop words in, our analysis would seem to indicate that all of our documents are about the, and, but, right? All those little stop words that actually don't add a lot of value. So term frequency has some challenges. It's a kind of naive, I don't want to call it a naive approach, but it's a first approach. And I would consider your term frequency, a baseline, kind of like how your median, your mode, or your mean can be baselines, even if they're pretty blunt tools sometimes, right? Is that tracking on term frequency? It's our best guess without any more sophisticated tooling, right? If we see the word lamb show up 3 times in the sentence, Mary had a little lamb, the sentence is probably about lambs, right? But if lamb is in every single document, then it's not really adding new data, right? So some challenges. Term frequency starts breaking down a little bit. Okay. So term frequency mathematically is very direct. It's the number of times a word occurs in a document divided by the total amount of words, or total amount of time the word occurs in a corpus divided by the total amount of words, right? Very direct. The bag of words is in fact a term frequency represented as a vector. And so we can produce a bag of words very easily we make a string. My data preparation is pretty straightforward. I'm going to remove my commas and split the string. And if I make a series, a pandas series on those words and do value counts, then I get back a vector of counts, right? That's what value counts gives us back as a frequency. Okay, so bag of words has been around a good long while. It's been part of text analysis, automated text analysis for decades and decades and decades. But because bag of words is basically term frequency, it has those same challenges, right? Bag of words is a term frequency vector for every word, right? So bag of words is an okay place to start, but it does have those challenges. Word clouds are a visual bag of words, okay? So far, so good. Any questions on term frequency, bag of words so far? Cool. Now here's where we're going to introduce a new term called inverse document frequency. And let's just start with the definition or the takeaway. Like, why should we care about this new term called inverse document frequency? Well, it tells us it's a measure. So we get back a number, a positive number that tells us how much information a word provides in a corpus, right? And when I say corpus, I mean our body of text, right? So our corpus of blog posts from Codeup is our corpus, or our corpus of all of those InShorts articles is our corpus. Each article is a document, right? So with inverse document frequency, I'll show you all the math formula for it in just a second, but a higher number on IDF means that specific word, so every word has its own inverse document frequency, right? A higher IDF means that word provides more information. And that is to say that word is more relevant to a single document. As the number of documents that a word appears in increases, so we keep seeing that word over and over and over in multiple documents, then our IDF value will decrease at an exponential rate because of how the IDF formula is set up with a log. I'll give you an example. If we're looking at our corpus of Codeup blog posts and the word Codeup appears frequently, and it appears in every single document in our corpus, in our list of documents, then actually that word doesn't add any new or much new information in any individual document, right? If every blog post has Codeup showing up 5 times, then the word doesn't add new data if it when we add it, right? And that's really what IDF is all about here. Now, if we take another example, if the word scholarship or grant shows up a whole bunch in 1 or 2 documents, but it is not frequent across the entire corpus of documents, then we can come to the conclusion that the word scholarship conveys more meaning because it's shown up more frequently in a smaller number of articles. Those articles are probably about financial aid, right? And if we see scholarship show up on a new blog post coming in, then that new blog post is probably about financial aid, or it's giving more information, right? And this is really another way of looking at things that we might consider stop words, right? If we're looking at the Codeup blog posts, we might manually add Codeup as a stop word because we know that it's going to be just like peppered on every single page, right? So inverse document frequency it's a number from 0 to I don't think there's a maximum here, but we see that. So let's take a look at this chart here to get an intuition for IDF. Our y-axis here is our computed IDF value, right? And then our x-axis is a count of the number of documents each word appears in. And what we're looking at here is one curve for one word, right? So let's say this word is Codeup, right? If the word Codeup on a bunch of blog posts appears in one blog post, and it's fairly frequent in that one blog post, then that word is adding more information, right? It's adding something of value that we can assign weights to in an automated way, right? And as we increase the number of documents that word appears in, notice our inverse document frequency starts to decline, and it is actually declining. It's declining pretty rapidly, right? This looks like an exponential decay. So think of it like a half-life.
So would a novel be considered a single document, like a novel of 500 pages, or?
It depends on, so it depends. What does that depend on? If you are only, let's say you're analyzing Harry Potter and the Sorcerer's Stone, and you're only analyzing that one novel, that's your corpus. But if you're analyzing the entire series of novels is your corpus. So you kind of get to define what your corpus is, and the organization of your work. Like, depending on how we want to break things down, we could say documents are chapters, or documents could be books, entire books, if we're looking at a series, right? Yeah. So there's not like a hard and fast rule here.
Okay, cool.
Yeah. With the stuff that we're working with, I would say our list of blog posts, our data frame is the corpus. Each document is one blog post on the Codeup blog post. If we were looking at, say, like scripts, dialogue scripts for a TV show, we might say that each episode is a document, right? Not each line an actor says, but each individual episode is a document, and then we can get every episode or would be the corpus, right? And if we wanted to change our level of detail and compare and treat seasons, if we had like a whole lot of seasons of a show, we could treat the season as a document and analyze it that way. And we could say, wow, the last season was really dark compared to compared to the first season, right? Yeah. So some flexibility there. I'll show you the inverse document frequency calculation. Here's the good news. You don't need to calculate any logarithms by hand, but we take number of documents over. So this is a little different than just that term frequency, where term frequency is measuring the number of times in the corpus. The document frequency, or inverse document frequency, is the number of documents. So in this case, the number of blog articles over the number of documents containing that word. And this is how we're giving more weight to documents where that word shows up in a smaller number of documents, and then we take the logarithm of that, and so we get this positive number that gets very, very small as each word appears more frequently in higher numbers of documents. It provides less and less data, okay, less and less information. Like, yes, it takes bits and bytes as that word shows up more often. But in terms of the weighting and in terms of our original problem, determining which words are important or not, the IDF will get us around this term frequency problem of overweighting stop words and common words, right? We put these two things together. So the inverse document frequency is super useful, but see how the inverse document frequency is not taking into account how many times a word shows up in a single document, right? So the way that we bring that in is we take the product. It's pretty straightforward. The tf-idf here is the product of the term frequency number for a given term times that word's inverse document frequency. Okay. And so this is going to give us a single number. And what that single, or actually what this will actually give us a matrix for each number. And in this, because it doesn't quite make sense to talk about tf-idf in terms of a single value for a single word without talking about a specific document, right? So let's see. In the curriculum here, my notes that I'll be adding, committing, and pushing and all that good stuff are introducing the same terms. In the curriculum, there's a section on how to calculate tf-idf by hand. And that would be useful if you want to be able to do this by hand. In my lesson, however, I'm going to jump straight into sklearn and have the computer do the math for me. Because why not, right? The biggest takeaway with tf-idf, and I want to put some context in here, the so what, right? The so what, why are we bothering with tf-idf? And of all of the possible topics in NLP modeling we could teach, why are we teaching tf-idf today? Well, the number one thing is determining what a document is about it's both valuable and it's challenging. Term frequency is super sensitive to noise and it's imprecise. And when we look at tf-idf, it's pretty good stuff. tf-idf on the Wikipedia article, check this out. Survey conducted in 2015, so that's a couple of years ago now, showed that 83% of text-based recommendation systems use tf-idf. So that's a lot, which means that we have all been living under some regime of tf-idf in our lives already. This could be autocomplete, could be a tf-idf thing. Grammarly or syntactical checking tools are relying on tf-idf as well. Super frequent, right? Super frequent. So and if you get into this Wikipedia article, if you're really interested in the guts of tf-idf, check out that Wikipedia article. There are linguists trying, when I say linguists, I mean people who study a language outside of NLP. They're trying to find out why the heck the tf-idf is useful, because there have been some challenges to it, in some circles are like, okay, it works and we don't know why, depending from a linguistic point of view. From a machine learning point of view, we look at it and we're like, okay, we're getting weights of things, right? Getting weights of things. And that's the math way of talking about how important something is weights, just like weighting on a grade, right? Or weighting a stop word as 0 by deleting it. All right, cool. So I want to open up for questions at this point before we get into the code on our new characters, term frequency, bag of words, inverse document frequency, and then tf-idf. Is this tracking from, at least from a gut check and an intuition? The more a document shows up, or the more frequently a word shows up, is a good place to start. But just like mean, median, mode, it's not the whole story. And the more documents it appears. And I think it may be counterintuitive at first, but when we think of a concrete example like those Codeup blogs, like the word Codeup doesn't add new data because it's showing up on every document, basically, multiple times, right?
Yeah, it's reading the search engines, like Google uses tf-idf. When people search, they really value term frequency over just counting keywords. I thought that was really interesting.
Yes, in the olden days of Google, they did start with bag of words, and other search engines started with bag of words. And what you get if you build a search engine out of bag of words is people will dump the whole dictionary on their webpage and just paste it 100 times, change the font to the same color as the background color. And that was the first search engine hack, one of the first search engine hacks.
Yeah, remember at the bottom of web pages, real estate websites, and have like 1,000 keywords. And like people like do this, put at the bottom, like you'll score high. It was so ugly.
Yeah. So yeah, bag of words gets you, I don't know if it's airborne, but at least gets you off the ground. But it's pretty problematic. You know, if you put real estate on every single one of your web pages on a web page for like a brokerage, we already, you know, every new time the word real estate shows up on a new page doesn't add new information. But if there's something like talk to your agent about a tax credit, shows up a whole bunch on one document, but it doesn't show up on other documents, those words will convey more meaning, right? Awesome. It sounds like y'all are jiving. Sounds like y'all are in a good place on this. I'll move into the code. Let's do that. What I'm doing in my code is a little bit different than what's in the curriculum. What's in the curriculum is going to be a binary classification on spam or not. And what I'm going to give y'all as a comparison is a different data set. So I'm going to introduce y'all to a nice little data set I've got here. It is all of the next generation Star Trek lines. So this is my corpus. It's something like just shy of 300 episodes. And when we look at the shape of this, I think it's like 58,000 lines or something like that. Yeah, 52,000 lines. And there's a lot of characters here. And what I'm going to do with this modeling is I want to train. So we're going to do our text preparation in here, right? But I want to make a predictor that takes in a line and predicts what character said that line. That's my end goal here. When we're looking at the curriculum, the end goal of the modeling here is predicting if a given message is spam or not. So I'm doing something just a little bit different than that binary classification. Okay. So I've got a nice little CSV that I made on another project. I copied it over. It's not too big. It's like 5 megs or something. So it's in GitHub. When you can pull this down from the repo. It's already there in case you wanted to follow along. So is the notebook in case you wanted to follow along. What I want to do to reduce some noise here is grab the top 15 characters. So I'm saying, hey, give me the data frames character, do the value counts, and grab the first 15 characters. Because there's a lot of characters with one line that I want to avoid. Because it's hard to stratify when you have only one observation of something. Okay, so we've got a nice little data frame. In my analysis, I'm not paying attention to the episode name, at least in this draft of the analysis, but I am very largely focused on the lines in order to determine who is saying those lines, right? So what I'm going to do is bring in my happy little split function, and I'm going to split my data into train, validate, and test, as is our custom, right? And we'll do a little head there to show that, okay, we've got everything going. I realize I need to put a cleaning function in here because I've got like new line characters right next to the word captain's log. So let me do that real quick. Let me go grab a cleaning function super quick. Okay. Hey, there's a clean function.
And if you wouldn't mind, Ryan, could you scroll up to the top 15? I didn't get everything on that song.
Mm-hmm. Yeah, there's a lot of there's a lot of characters that only have one line. So right now I'm just focusing on a subset.
I already got a screenshot of it.
Okay. Well, the code is also up in GitHub too. Did you have a question about anything about my logic on here?
Oh, I don't think all of this was pushed up because I went ahead and pulled it. And it goes from the TNG to the split. That's why I was like, oh, I need to post that in there. All right,
okay.
Cool. Thanks.
Okay, cool. I might have changed it a little bit, but y'all will have a copy of this. What I'm doing here is the value counts. I'll break this up a little bit. So if we do tf.character value counts, we get a series where the index is the character, and we have the frequency on the right. And if we grab the index with the slicing syntax here, we can look at the top 20 characters, for instance, or the top 15 characters. And so that's what I'm doing. With this dot is in, this top 15 characters, I'm sending a list. So I'm saying if the character exists in that list, then they're part of that top 15. Okay. Let's see. I've got my clean going on here. I should probably clean my data before I start doing much else with it. So I'm going to do that. I'm going to do df.line is change this just a little bit. So return a joined string. df_line is df_line.apply the clean function. And then we'll take a peek at our data here. So I'm applying this cleaning function, takes in a string. I modified it ever so slightly from what was on the Explorer to turn this list of strings into a single string. So now we no longer see the \ns, and we've lost some stop words. Okay. And in my clean, I decided to do the lematizer so that I could have, I like the lematizer because if it encounters a word that it's never seen before, like a proper word it's never seen before, like, in some sci-fi series, there's probably words that the WordNet lematizer hasn't seen. If it encounters a word it hasn't seen, it leaves it alone. The logic behind that is that it's a proper word that it just hasn't seen before. But we'll lematize everything so we don't have just some chopped up stems. So we've got our clean, inquiry, word, snoop, right? We'll split our data here into train, validate, and test. And if I wanted to focus on the episode, I'd have to encode this episode name column. I'm gonna skip this for now. I'm just gonna focus on lines and characters, right? And so I will say set up our X variables, okay? And then we'll set up our Y variables. And here's the part that's new. Okay, here's something new, is this tf-idf vectorizer. You may have noticed that when we look at xtrain, this is all text, right? Everything that we've been doing with text so far has been working with discrete variables. I mean, as far as modeling, we've had to take text, turn it into a discrete variable. Well, think of this tf-idf vector as doing a one-hot encoding on all of the words for us. It's handling that encoding for us. And it's gonna produce a matrix for, each line. And our pattern with sklearn is make the object, fit the object on our training data, and then use the object. So this vectorizer, it's not a scalar, right? But what it is basically, it's an encoder. And we've done encodings before, right? We did the one-hot encodings with discrete values before. But now we're not dealing with discrete values that are like 5 or 20. We're dealing with discrete values of every single individual word, right? So these vectors are pretty sparse. They're kind of gnarly to look at. But we will create an empty vectorizer, and then we will fit it on xtrain, and then we will transform or xtrain, xvalidate, and xtest so that they all have been vectorized. When we look at this, let's take a look at xtrain vectorized real quick. It's a sparse matrix, and all that means is that it's an array with lots of zeros, lots and lots of zeros. Right, that's what sparse means as opposed to dense. And in here, let's see, there is a method called toDense. So we could, because this is sparse and NumPy doesn't want to show you thousands of zeros, we have to do a toDense to see what it looks like. So lots of zeros. It's not very exciting, right? Not very exciting at all. Sparse vectors or matrices, tons of zeros. Okay. So really our data prep here, I'm skipping the explore and the stage. But my prepare, I clean the strings. I realize I probably should have added a tokenizer here to get rid of some of this other junk. But here's the part where something new is really something old that you already know how to do repackaged. So now that we have a vectorized data set, we can use our classification tools. We can use things like a logistic regression or a random forest or a decision tree. And why I'm going for classification algorithms here is because I'm trying to predict a discrete outcome. I'm trying to predict the character based on their lines, right? And in all of our classification work before, all of our machine learning before, we had to turn our words into numbers, right? And our tool doing that, our new tool, I hadn't seen this before, is this tf-idf vectorizer. And this doesn't make sense to you because it's vectorizing on that tf-idf formula. There's no other need outside of NLP for this tf-idf vectorizer, right? So just to give you a sense of how vast this is, toDense.shape, 13,000 columns, right? So that's basically every single word has a column, right? That's why most of these are zero, because most of any single given word probably doesn't show up everywhere, right? So here's the cool part. I'm going to make a logistic regression model, and then I'm going to fit that. So make the thing and then fit it. Fit the classification model on our vectorized training data. Now we have a logistic regression, right? And look at that, it's taking a little while. When we did logistic regressions before, they might not have taken 4 seconds or 3 seconds, right? So I've got an empty logistic regression model, and I've decided to do logistic regression because I want a percentage, right? So now that we have our trained model, again, modeling is like kind of the anticlimactic, right? I'm going to make a data set that holds all of our actual data. Remember, we're using supervised learning here, right? Classification is a supervised learning approach. So I have my actual. Now I'm going to get my predictions. So use the X values and the trained model, or use the trained model to predict y given the input x values. Let's vectorize inputs of x. Right? So let's do that. And we can take a look at the train here, and we're comparing actual versus predicted, right? So the actual column is literally what the label is, because we have labeled data because supervised learning. And then our predicted column is what our logistic regression is predicting. Our logistic model here, right? And now we could pull up a classification report if we want, or we could pull up accuracy, which is pretty straightforward if we've built this data frame already. So my training accuracy is 54%. And that's not like, I don't know if that's amazing or if it's terrible, but it's certainly better than randomly picking 1 out of 15, right? If our baseline was to go with the most common line comes from Picard. So we'd have a lot of false positives. If we just picked randomly, our chances of picking correctly would be 1 out of 15, right? So there's our train accuracy. We can take a look at our out of sample accuracy. Is a little bit less, quite a bit less, which means our model's overfit. And you'll notice I didn't do any model tuning. I didn't make a feature out of the episode. I bet you if we made a feature out of the episode, it would crank up this accuracy quite a bit. But now, if I've got this model, and it's not like in the 90%, but let's see how well it measures things, how well it predicts. So now that we have a trained model, let's use our model to predict the author or the character of any given line. So here, I made up some lines, just thinking, okay, somebody on a ship must say something about responsibility. They have phasers, set phasers to stunning. There we go. And then the warp drive is about to go critical. We'll figure out who said that. What does it mean to be human? I cannot calculate feelings. We're going to make a prediction about that. Romulan bird of prey decloaking off the port bow. Who said that? Feelings and chocolate. We'll see who's talking about feelings and chocolate here, right? So who's talking about war? Who's talking about feelings? Who's talking about responsibility? Who's talking about phasers? You'll notice right here, this is really, really, really important. We have to vectorize. We have to vectorize these inputs. The classification model, because the classification model was trained on vectorized data, so it has to make predictions on vectorized data, right? And here we go, drum roll please. Shouldn't be too big of a surprise. Even with a model that overall is 54% accuracy, it's predicting that first line is coming from Picard. The second line is coming from Riker. LaForge, head of engineering, is talking about the warp drive. Data is talking about not being able to calculate feelings. Worf's letting everybody know there's cloaked ships, and Troy is a big fan of chocolate. So this is how we can make, like if we had if we made like a web page or something where we could say, type in a sentence and predict who said that sentence. This is the code that would run, that we would have run right here. We would deploy the trained model, put this into production, and then we need to clean. And I realize I didn't clean these new data, these new sentences. All I did was just vectorize them. So we could probably do. Let's clean them just to be clean here. Lines as lines dot apply the cleaning function to them. Look at that. After cleaning, our prediction changed on this first one. We have a responsibility. So we removed some noise in there.
Can you predict accuracy per character? Like I feel like data, you know, might have a really high accuracy, right? Just based on how like his dialogue, right?
Right. I'd be willing to bet that if we took our data set here, I'm going to focus on train. And if we just do, let's talk about Sweater Boy, right? Wesley. And so we say train oh bother. Let's see. Train dot actual is Wesley. So we get a subset here, right? Now, this data frame is only the observations where this was Wesley Crusher's line, and we can compare here. We can do, so Wesley actual, Wesley dot predicted. Mean, this is my one-liner for accuracy. So it's not very good at predicting Wesley. It's pretty rubbish at it, actually. What about, oh, this is fun. How many times have we had a variable called data? Right. Data is actually a plural word, the plural of datum. And American English started changing somewhere around the 80s and 90s to talk about data as a singular term. It's kind of interesting how that coincided. But let's take a look at how well it predicts on data here. I'd be willing to bet some of these are much more accurate. Yeah. So it's much better at predicting data, the data character. Let's see, who do we have here? Crusher. Let's see what the doctor is talking about, how well it predicts the doctor. And we could loop through this, right? So we don't have to just keep doing this manually. All right, not great accuracy on the doctor. Right. Also, if accuracy is not our only metric with classification, right? We can also pull in our classification report. I don't think I had the classification report in my import, so I'm going to import it now. And then we will focus on the train actual and train predicted. And, oh, hey, look at that. Okay, cool. So our overall accuracy for everybody is 54%. And with a nice little loop, we could put together something that gets the accuracy for every individual here. And when we look at our different metrics, precision and recall, depending on if we're focused on minimizing misses or minimizing false positives, then we can say, oh, we've got really good precision on predicting the line coming from the computer. And that's not too shabby. That's not too shabby. We could probably do for a character in so we can get our characters here. in characters, we can do what we just did, right? We can say character lines is train where train.character, the column character equals our variable character, right? And then we can do, we should probably do a little print or something. Character lines actual is character lines predicted, and we can get our average in here. So we can probably do out our character. Oh, this is actual train dot actual is the character. Character lines actual, character lines predicted. Oh, bummer. What am I doing wrong here? None type. Run it once. Okay. So character lines is what I think it is. We'll throw a break in here. Oh, it's all the parentheses. Rather than fixing my problem real quick, let's talk about it. I tried to print something, right? I printed out a whole bunch of truths or a whole bunch of Booleans, but we can't take the mean of a print statement. So I'm trying to do too much on one line, right? What's the return value of a print? 100% of the time.
None type.
None type. It's lies, all lies, right? So because it's just a little bit of a parenthesis balancing issue, let me make a variable. Variables are basically free. They cost a little memory, but no big deal. We'll do our calculation up there, and then we'll print our accuracy. There we go. So we can print, oh, we can clean this up a little bit. Print. Predicting character as we'll probably round this to, we'll do a nice little rounding here. String. There we go. So predicting Picard, 88% accurate. Predicting Q, it's not good at predicting Q. Nobody is. All right. And depending on how we can, on what we're focused on, we could bring in different metrics here, right? Cool. Yeah, larger roles do have a higher accuracy. This is also this is a bit of an imbalanced data set, right? If we were to look at least our train data set, this is fairly imbalanced, right? Picard is 5984. Out of 21,000. So it's a little bit unbalanced here, right? And we see that the number of lines is decaying. It's shrinking quite a bit. But yeah, if you have more training data you have more observations, then yeah, we can generally have better models with more observations. Cool. So, yep, I'm not going to go try to shop this to Universal or Paramount or anything, but the idea with this approach here was to connect this wild new stuff that we're doing with words. And for the first time, we're actually like working with words as words. But as soon as we're done with our explore stage, we bring in that tf-idf vectorizer, and this is turning our sentences into numbers for us. It's encoding everything. It's working. It's doing, this vectorizer is doing two things. I'll put it in the steps. Step one is creates tf-idf values, or calculates for each word, and then for each word for each document. And then step two encodes these values so that we can use models that only work on numbers, like classification models. This also means if you've vectorized your business over here, you can do clustering, right? You can do other models now that you've vectorized your text, your corpus. I always vectorize my business. Yes. I love it. I went off the curriculum. Like, you'll notice that the guts of this notebook mirror the curriculum very, very closely. The big thing that's changed is, instead of predicting ham or spam, which is a binary classification, I wanted to predict characters. So wanted to give y'all something just a little bit different. All right, I'm gonna stop my share here and open for questions at this point, y'all. All right, it's totally cool. If you have questions that come up later, that's great. I'm going to add, commit, and push my stuff right now.
Sorry, just
go ahead.
So I think one of the problems that I had with yesterday's data was the fact that it was all like paragraphs, and I had to break it down into a list of words. So could we also use that on yesterday's, like on our articles?
Yeah, looking at what we can do with this. We could try to predict the category of an in-short article given its text. That would be something that we could predict. With the Codeup blogs, we might be able to do some manual labeling and make a classifier if a blog is data science or web dev or something else. That would be another classification option. What I would also recommend is working with that spam data to build a spam predictor. So you can follow those same steps, feed it a text message or feed it a string, and then get a prediction if that's spam or ham. Yeah, that's something that comes up quite a bit in larger like NLP projects, is what happens, or larger ML projects, what happens when you want to do supervised learning but you don't have labels in the data already. It's actually a pretty frequent occurrence. It's so frequent that some people in the space, their job is to label data, right? and depending on their analytical skill set, they might do clustering if they know how to do clustering to try to answer that question and make labels. But I bring that up because the Codeup blogs, there's not like a label there already, so you might have to make a label or manually add one. The in shorts, I'd say that the label would be the category.
Have you looked at this data set using like random forest or decision trees?
I haven't. No. And different models may be more effective than this logistic regression.
But it would be possible to use any of those types of classification on this or anything. Okay.
Once you vectorize this data, y'all, you can do clustering with this, and we can see, I mean, clustering on text data is something that is frequently done to determine authorship, right? So you could do clustering on text, you could do classification on text, and any kind of classification tool as well.